The next concept that we're going to talk about with solutions is diluting them. So in these notes, we're going to talk about how you can take what's called a stock solution, like a highly concentrated solution, and make lower or lesser molarities from that stock solution. And then we're also, at the end of these notes, going to talk about how molarity can be incorporated into the fun of stoichiometry. So let's get started. All right, so like I said, first thing we're going to talk about is how you dilute a stock solution to get a certain molarity that you need. So a stock solution is an already made solution of a relatively high concentration. So we can use these stock solutions to prepare more dilute or less concentrated solutions that we might need. Now the interesting thing about dilutions is that even though we're putting more water into them and diluting them, the total number of moles of the solute doesn't change. We don't take out moles and we don't add moles to it. So the total moles of a solute does not change during dilutions, and we'll see why in the next slide. This is the formula that you use for diluting stock solutions. M1 times V1 equals M2 times V2. And I've put down what these different variables mean. So M1 is the molarity of your original stock solution. So you have to know how concentrated your stock solution is before you start diluting it. V1 is how much volume of that stock solution is needed to make the new solution. M2 is the molarity of your new or diluted solution. So you have to know what molarity you want to make. And then V2 is how much you want to make of it. Okay, it's got to be the volume of the new diluted solution. So in the previous slide, I said that the number of moles does not change when you dilute, and this is why. If you remember, to find moles, you have to take molarity times liters, right? So that's molarity times volume. So if we have molarity times volume of M1 V1, and we have molarity 2 times volume 2, okay, they're equal to each other, right? And if molarity times volume is the number of moles on the left are the same as the number of moles on the right. So that's why the number of moles of the solute actually does not change when we dilute something. So it's kind of an interesting fact there. All right, so let's take a look at an example. It says if you have 1 liter of 5 molarity NaCl, how much of it do I need to make 1 liter of a 2.5 molarity diluted solution? Okay, so we've got our different variables. Our M1, right, we see is 5.0 molarity right here. Now our V1 is what we actually want to solve for, because it says how much of it, right, do I need? That's what we need to solve for. So a lot of times when you have these types of questions, it will give you how much you have in the beginning, but we actually don't need that. So it's kind of there to trip you up. So I'm giving you a heads up right now. If it tells you, you have got 2 liters of this molarity solution, how much do you need of it? You don't need to use that number, okay? All right, let's see. M2 is, well, we need to make a 2.5 molarity solution in the end, and it says that we need to have 1 liter of it, okay? So we have our variables set up. Now let's put them into our equation. Remember, our equation is M1 times V1 equals M2 times V2. So we have the molarity of the first one, 5.0. And remember, we're trying to figure out how much volume of that we need. And then our ending molarity is 2.5, and we need 1.0 liters of that. So when we do this math, right, we'll divide this side by 5, this side by 5. So we're going to have 2.5 divided by 5, which is 0.50 liters. So this is how much of the stock solution we need to start with in order to make 1 liter of the other solution. So we need to have a half a liter, 500 milliliters of the stock solution, and then we can add water up to 1 liter to make 1 liter in the end. So we're going to have 500 milliliters of the stock plus 500 water to get our new solution. So that's how the dilution problems work. So the trick for these is to identify each of the variables that you have that you're given in the question, and then solve for what you need. So that's what we're going to do tomorrow when we're in class and we've got a whole bunch of practice problems. And then you're also going to do that in our lab as well. You're going to figure out how much stock solution that you need, and then you're going to make certain molarities of solutions from there. So now let's take a look at our second question, tying molarity to stoichiometry. Fun. All right, so here is our second question. How do I solve stoichiometry problems with molarity? All right, okay. So if you're given volume and molarity of a substance, okay, in a chemical, you have to be given a chemical reaction for it to be legit stoichiometry, right? And in the question, you'll be given the volume and the molarity of the substance rather than moles or grams. But now that you know the molarity triangle and the molarity formula, you can use the volume and the molarity in order to solve for moles. That's our first thing that we're going to do. So you take the volume and the molarity, times them together, and you get the moles of the substance. And then likely you'll be asked for, moles or grams of a different substance in the reaction. So that's where you're going to use your stoichiometry bridges in order to get to your final destination. So let's take a look at this example. It says if 350 milliliters of a 0.5 molarity NaCl are added to KBr, how many grams of KCl will be produced? Okay, so we've got 3 different substances here, okay, that we have in this one question. So we definitely know it's stoichiometry if you've got 3 different substances you're talking about. All right, so we are given 350 milliliters of a 0.5 molarity NaCl. So that's what we're given, and so that's the volume and the molarity. And then we need to figure out how many grams of KCl is going to be produced. So again, this KBr we don't need to worry about because we're not given anything from him. Okay, the only thing that serves is to know that KBr is in the question or in the equation when we, if we have to actually write it out. Okay, so here's our reaction that we're given, and we've got our question. Now let's start solving it. So first thing to do, if we have volume and molarity, is to find the number of moles. So we're going to find the moles of NaCl, right? By timesing the molarity, which is 0.500, times the liters. Remember, to solve from milliliters to liters, go 3 spots to the left. So we're going to have 0.350 liters, okay, and that's going to give us 0.175 moles of NaCl. Okay, all right, so we know we've got 0.175 moles of NaCl. Now it's asking for grams of KCl. So this is a mole to gram, so that's 2 bridges, right? So let's draw our 2 bridges. And we're going to start out with our moles of NaCl. And so moles of NaCl go down here to cancel, right? And our final destination is grams of KCl. So if we have to go to grams, that means we've got to have moles of KCl first. So that goes there in the middle. Okay, so hopefully you guys remember how to do this, and if not, then you gotta get it going, because this is not the last time we're going to see stoichiometry. All right, let's plug in our numbers. So we've got 0.175 moles of NaCl. Okay, here in the second part we have a mole to mole ratio, and we've got 1 mole here and 1 mole here, so that's 1 to 1. And in the last part, we're going to figure out how many grams are in 1 mole of KCl, and that is going to be 75 grams. So then we just use, or do our math, okay, multiply everything on top, divide by the bottom, and we'll get our answer. So our answer is 13.0 grams of KCl. Okay, so we figured out our grams of KCl, okay, from just having the molarity and the volume of a different substance in the reaction. So we're going to have lots of practice problems tomorrow and kind of figure out how it works, okay? I do have one more scenario and question that has to deal with stoichiometry with molarity. So let's take a look. Okay, so in the last scenario, we were given the volume and the molarity. This time, perhaps you're given grams of a substance and you're asked for the molarity of a different substance in the equation. So it's kind of, opposite of what we did last time. So in this scenario, if you are given the grams of one substance and you have to find the molarity, you're going to first use your stoichiometry bridges to go from grams to moles of the other guy. And then you can use the molarity formula in order to solve for molarity. So let's take a look at this example here. It says if 25 grams of AlBr3 was produced when 125 milliliters of CSBr solution was added, what was the molarity of the CSBr solution? Okay, so again, here we're given our 25 grams of AlBr3, okay, and we are asked for the molarity of CSBr. Now to figure out molarity, we're always going to need liters as well, okay, the volume, and so we're also given the volume here. So we've got everything we need, we just need to figure it out now. Okay, so let's take a look. We've got the equation right here, so the first thing I want you guys to do is to take a second, pause, and balance that equation. Okay, hopefully this is what you came up with to balance it, and so let's take a look at the stoichiometry that goes along with it. So again, the thing that we're given here is 25 grams of AlBr3. So that's the first thing that we're going to do, is we are going to change the grams of AlBr3 to moles of CSBr, because we can't get anywhere with molarity without knowing moles. So it's a gram to mole, okay, a gram of one thing to moles of something else, so that means we've got two bridges. So we're going to have grams of AlBr3. So that means it's going to be down here as well to cancel. And we need to go to moles of CSBr. So to get from grams of AlBr3, we got to go to moles of AlBr3 so that we can have our mole ratio. Right, because every time you do stoichiometry, you have to have a mole ratio somewhere in your bridges. Okay, all right, so we have our units set up. Now let's take a look and plug in the numbers. So we are given 25 grams of AlBr3, and here in the second part of our bridge is moles to grams for AlBr3, so that's going to be 1 mole, and you got to add up the AlBr3 on your periodic table, and that's going to give you 267 grams in a mole. And then our last part of our bridge is the mole to mole ratio. So there we look in, remember, in our equation. So the coefficient for CSBr is 3, and the coefficient for AlBr3 is 1. So we have a 3 to 1 ratio. So we're going to multiply everything on top and divide it by what's on the bottom. So we are going to end up with 0.28 moles of CSBr. Okay, so that's how many moles of CSBr are made. Now, But we're not done yet because the question, right, is what is the molarity of CSBR? So we're not done yet. So let's take a look at the second part. All right, remember molarity is moles divided by liters. So what we'll do is we'll take our moles that we just found out, okay, of CSBR, 0.28, and we're going to divide it by the liters. And remember, we're given that up here in our equation. So we're given milliliters, so to make liters, we move it over 3 times to the left, and we're going to have 0.125 liters. So in the end, the molarity that we actually end up with in this reaction is 2.24, or actually just 2.2 here, molarity. All right, so that's the final molarity of our CSBR solution, and that's how we got it. All right, so just an extra little step of having to work with the molarity formula in order to figure out the molarities or the grams or moles of whatever in a stoichiometry situation. Okay, so that's all that we have for these notes, and we will see you tomorrow in class.